Hi, welcome back. Let's get started. We've been talking about special systems, and now we're moving into systems of inequalities. So, get some graph paper, pause me here if you need to, make sure that you have some handy. All right, a system of linear inequalities is a set of two or more linear inequalities containing two or more variables. So basically, it's just two sets of inequalities that are lines. The solutions of a system of solutions, plural, of a system of linear inequalities consists of all the ordered pairs that satisfy all the linear inequalities in the system. Blah, blah, blah. What does that mean? Let's find out. Example 1. Tell whether the ordered pair is a solution of the given system. Okay, so we've done this before. This should be review. So you're just going to take this ordered pair and you're going to plug it in to both of these inequalities and determine whether or not it's true. So for my first inequality, I'm going to plug in -1 for my x and -3 for my y. So -3 is less than or equal to -3 times, well, -1 plus 1. -3 is less than or equal to 3 plus 1. -3 is less than or equal to 4. Is this true? Absolutely. So it works for the first one. I'm going to put a little check to remind myself it works for the first one. For the second equation, I'm just going to do the same thing. -3 is less than 2 times -1 plus 2. -3 is less than -2 plus 2. -3 is less than 0. Is that true? Yes. Therefore, we would say -1, -3 is a solution. That's easy enough. We did that the very first day that we talked about systems of equations. So what does that mean for where we're going? Well, remember, an ordered pair must be a solution of all inequalities to be a solution of the system. So just like we just went over, since it fit both, since -1, 3 fit for both equations, it is a solution. All right. Here's a nice little thing. If you need to pause it and kind of take a look at this and kind of start understanding what it means, I'm going to explain it, but if you don't get it, pause it, reread, and just stare at it till you understand. All right, to show all the solutions of a system of linear inequalities, graph the solutions. So as you can tell, they've graphed these lines here, and they've shaded, just like we did when we graphed our inequalities, they shaded what it said was true. By shading what it said was true, where these two systems overlap, if your given point lies in where the shading overlaps, it is a solution. Let's find out what that really means. All right, here we go. We have a system that says -3x plus 2y is greater than or equal to 2. Well, this one isn't solved for y, so I'm going to go ahead and I'm going to solve this first one for y so that I can graph it. -3x plus 2y is greater than or equal to 2. I'm going to add 3x to both sides, giving me 2y is greater than or equal to 3x plus 2. Divide everything by 2. Y is greater than or equal to 3/2 x plus 1. So I'm going to graph this first line in red over here. I'm going to go up to +1. This is a positive slope of 3/2, so I'm going to rise up 3, run 2. I'm going to rise -3, run -2. And then I'm going to make a solid line because I know that a solid line means or equal to. All right, now for my second equation, it's already in slope-intercept form. So, oh, thank you. Miss Sokolowski just asked, are you going to shade that? Well, yes, I am. If y, let's go back right here to number 1. If y is greater than or equal to 3/2 x, I'm shading above. So we're talking about everything on this side of this line is a solution. All right. So now I'm going to I'm going to graph and shade for my second one. Now the very first thing that I take notice of here is that this is not or equal to, so I know my line is going to have to be dashed. So I'm going to go to positive 3. My slope is 4, so I'm going to rise up 4, run 1. I'm going to rise negative 4, run negative 1. And do what? Oh, thank you. 1, 2, 3, 4, 1. If Miss Sokolowski wasn't here, we would have one terrible lesson. Hold on, bear with me. 1, 2, 3, 4, 1. Okay, here we go. My line is dashed, so as I draw this line, I'm going to make sure that I remember that I'm talking about all points not included in the line. Now it says y is less than. Well, where do I shade if I'm talking about y being less than? Yes, I shade on this side. So now I have to ask myself, okay, I've got some crazy shading going on. What does that mean? Well, I want to talk about everything where it overlaps. So I see that we're talking about everything in this black area. So any point inside this overlapping section is a solution. Let's pick a point inside that overlapping solution and let's check it. So I'm going to pick the point 1, 3, which should be right there. It's inside of the overlapping solution. Let's check the point 1, 3. So coming back over here, 3 is greater than or equal to 3 halves times 1 plus 1. 3 is greater than or equal to 3 halves plus 1. Well, I know that 3 is greater than or equal to, that's 1 and a half plus 1. 3 is greater than or equal to 2 and a half. Is that true? Yes, it is. So it's true for the first one. Let's check it for the second equation. Y, which is 3, is less than 4 times 1 plus 3. 3 is less than 4 plus 3. 3 is less than 7. Yes. So this point is a solution to both. Notice that it lies in the overlapping area right here. I know.
So something that's in the red or something that's in the blue, if it's just in the red or just in the blue, it's not a solution then?
It's not a solution. It can never be a solution if it's just in the red section over here. Not a solution to both. If it's just in the blue section over here, not a solution to both. Anything in this little bitty area where they overlap is a solution to both. I know. Let's try again. It seems like a lot, but it's really not. All right, so let's graph this system using shading to determine if they have a crossing shaded area. So the first one is y is greater than x minus 7. I'm going to graph y is greater than x minus 7. My slope is 1, up 1, over 1. And I see that this is a plain old greater than, so I'm just going to make a dashed line. And I notice also that it's talking about greater than. So I'm talking about everything in this graph that's in the shaded area. This is when I wish that my pen was bigger.
Yes.
I could shade more at once.
Okay, guys, just remember, anytime it's greater than, that means you're going to shade above the line. So she's shading above the line here. What's on the line is not included.
That's right. Anything on this dashed line right here is not included. So for my second equation, I need to solve that and put it in slope-intercept form. So the first thing I'm going to do is rewrite. I'm going to subtract 3x from both sides. Sorry. So 6y is less than or equal to negative 3x plus 12. Divide everything by 6. Y is less than or equal to negative 1/2 x plus 2. So I'm going to go over to my graph and I'm going to graph this inequality. So positive 2, that's my y-intercept. Negative 1/2 is my slope. If I rise up 1, I go to the left 2. Go back. Do this side. So now I have to check. Is this solid or dashed?
Solid.
You're right. It's solid. So I'm going to draw my solid line here. Am I talking about everything above the line or below the line?
Below.
Below, because it says less than. So I'm talking about everything. Ms. Sokolowski, am I talking about everything on the line too?
Yes. Everything on the green line.
But not on the blue.
Not on the blue line.
Okay. So here where I have my two overlapping sections, I have all the stuff, everything on this line, not on this line. Everything inside here is a solution. This is a solution. You're more than welcome to pick any point on here. And why don't you right now just pick point 0, 0, because that's really easy and that lies in both, and plug it in and check to see if it works.
And just the same, I could pick something that was not in my shaded region. Like I could pick this point right here, and I would want to make sure that I get not a solution when I plug in this x right here, because that's not included in my shading. So sometimes it might not be a bad idea to check something that is in your shaded and something that's not in your shaded, especially if you're not sure of the overlapping area. Never hurts to do more.
All right, so right now let's review a couple of things that we've learned. First of all, graph both lines. Make sure that you're checking to see, what am I talking about, or equal to, or just greater than or less than, because that's very important. Also, remember if I'm shading greater than, I'm shading above, less than, below. Okay. Here we have another one. Well, maybe this one, I see something very interesting about this. We talked about special systems, and you all should notice something very special about this as well. I noticed that these
same slope.
Have the same slope. So let's see what happens here. If I have y.
I know they're going to be parallel.
Okay, so you know they're parallel. 1, 2, 3, 4. I'm shading. I'm going to do this first one. My slope is 2x. Negative 2x. Sorry. 1, 2, 1, 1, 2, 1, 1, 2, 1, 2. And I'm talking about a solid line, so. And I'm also talking about everything that is less than this line. Everything that's less than or beneath this line. Okay, my second line, I notice, has the same slope. It starts out at positive 5. 1, 2, 3, 4, 5. It has a slope of negative 2, just like our other one. You can already see these lines are parallel. And it is a dashed line. And I'm talking about everything that is greater than this. All right. Do we have any overlapping shaded areas?
I don't see any.
I don't see any overlapping shaded areas.
What could that mean?
That could mean only one thing. That there are no solutions.
No ordered pair will make this true. Like none in the whole world will make this true.
None ever. Now I could pick any point on my whole graph and plug it in, and it's always going to be not a solution.
All right.
Okay, so let's look at the next one. Oh my goodness, Miss Sokolowski, I noticed something special already.
Parallel again.
These have the same slope. They're parallel lines. So I'm going to graph these. I'm going to graph my first one here. Y is greater than, starting at negative 2.
Now, some of you that think you might know the answer to this already, just hold on a little bit. Don't skip forward.
Yeah, why would I show you the same thing twice?
I don't know.
So I see that it's a dashed line. So I'm going to graph this dashed line, and I see that it's greater than, so it's talking about everything on this side of the line. Am I talking about the stuff on the line?
No.
No. So now for my second equation, I see that I start out at positive 6. 1, 2, 3, 4, 5, 6. My slope is 3. 1, 2, 3. Wait, 1. Sorry. 1, 2, 3. 1, 1, 2, 3. 1, 1, 2. And I see that it's also one of those special dashed lines. That means I'm not including the line. And I see that it's talking about everything that's less than. So it's talking, thank you. It's talking about everything that's less than or on this side of the line. So, sorry, my brain was already processing that this area in the black
Is the overlap. Where they overlap.
is where they overlap. So anything in the black shaded area is a solution.
But what about something that's on either one of those lines?
If it's on the line, remember we've got these special dashed lines because we're talking about greater than or less than, not greater than or equal to and less than or equal to.
Right.
So if it's a point like right here on this line, we cannot include it.
Right.
Okay. Couple more. Last one. Hang in there. I see something special here too. They've got this same slope thing going for them. So I'm going to graph the first line, positive 6. My slope is 4. I'm talking about or equal to. So this is a solid line. All right, my second.
I'm going to shade that one
Thank you.
above.
I'm going to shade above this line because I'm talking about everything that's greater than. Then I have my second line here in blue. Same slope. And I'm also talking about a solid line. And I'm talking about everything that is greater than. So now I see something very interesting. I see that it's only overlapping on this side of this line.
So from the green line over.
Yeah, Ms. Sokolowski, what do you think about that line? Do I include that line or do I not include it?
I think you should, definitely, since it's a solid line. If it was a dashed line, then no. But since it's a solid line, the green line should be included.
So everything, including our green line, and to the left over here is where they overlap, and therefore everything over there is a solution. Thank you guys for hanging in there. I know it seems like a lot and you're overwhelmed. Please remember to take good notes so that whenever you come back in tomorrow, we can work out the kinks. Y'all have a good night.